Hello. In the previous section, we discussed about a RLC circuit with no forcing function, that is, without any source connected. The working of the circuit essentially is a transient activity. We saw that the instantaneous voltage and current in the circuit will have a phase difference and both will damp out in time according to the value of the resistance included in the circuit. From this section onwards, we try to understand the phenomenon happening in circuits with various combinations of R, L, and C, which are connected to a AC voltage source. We shall begin our discussion with a series RL circuit connected with an oscillating electromotive force. So, in the circuits that we are going to discuss, we will apply an oscillating electromotive force having frequency F, which is expressed in cycles per second or hertz. Now, the angular frequency is defined to be omega equal to 2 pi f, which is expressed in radians per second. Our prime motive in this study is to determine how the current behaves in a RLC circuit when an oscillating voltage is applied in the circuit. Alright, so this is a RL circuit with a sinusoidal input voltage E equal to E0 cos omega t. You can see that the inductor and the resistor are connected in series and the current that is flowing in the circuit is designated as I. We want to write the equation governing the current. The voltage that is applied in the circuit is E0 cos omega t. And this creates a voltage drop of L times di by dt across the inductor and a voltage drop of Ri across the resistor. So E0 cos omega t is equal to L times di over dt plus R times I. Let us denote this by equation number 1. As we switch on the circuit to apply the voltage E0 cos omega t, there will be some transient behavior depending on the initial conditions. But the transients exist only for a short period of time. Since we have applied an oscillating EMF in the circuit, that will generate an oscillating current, and we want to know the nature of the voltage and the current when a steady state has been reached. We want to analyze whether the voltage and current are in phase or there exists any kind of a phase difference between the voltage and current when the steady state has been reached. So that is what we are going to analyze. So our circuit has a series inductor. Because of the presence of the inductor, the instantaneous current in the circuit, which we designate as IT, can be assumed to have a phase difference of phi with respect to the applied voltage. We have written the instantaneous voltage as E equal to E0 cos omega t. Now, the instantaneous current IT, this would be equal to I0 times cos omega t plus phi. That is, we assume that the voltage and current oscillations have a phase difference of phi. Now, we want to find the constants I0 and phi. For that, what we will do is that we will substitute equation 2 in equation number 1. So when we do that, it will be L I0 minus sine omega t plus phi multiplied by omega plus R I0 cos omega t plus phi equal to E0 cos omega t. When we rearrange this equation, it will be negative of L I0 omega sine omega t plus phi plus R I0 cos omega t plus phi equal to E0 cos omega t. In the next step, we have to separate out sine omega t and cos omega t. For that, we'll make use of the trigonometric identities for sine a plus b and cos a plus b, and we will expand the previous equation as minus of L I0 omega and then sine of omega t multiplied by cos of phi plus sine phi cos omega t. So this is the expansion for sine omega t plus phi, and then r I0, then we are going to expand cos a plus b, that is cos omega t plus phi, that is cos omega t multiplied by cos phi minus sine omega t multiplied by sine phi. This is equal to E0 cos omega t. Now we'll set the coefficients of sin omega t and cos omega t separately equal to 0. So that will give us two equations. The first equation is negative of L I0 omega, then cos of phi minus r I0 sin phi equal to 0, and the second equation is negative of L I0 omega sin phi plus r I0 cos phi minus E0 equal to 0. We'll keep this as equation number 3 and this as equation number 4. And when we rearrange equation number 3, we'll get tan phi as equal to negative of omega L over r, and then from equation 4 we'll get I0 as equal to E0 over r cos phi minus omega L sin phi. We will simplify this equation, that is E0 over r multiplied by cos phi plus tan phi sin phi because tan phi is negative of omega L over r. So that this equation is E0 cos phi over r. Now we have to substitute for cos phi. For that, we multiply and divide equation number 5 by the square root of the sum of the squares of the coefficients of sin phi and cos phi in equation number 3. This is equation number 3, and the square root of the sum of the squares of the coefficients of sin phi and cos phi is given by square root of r square plus omega square L square. That is tan phi equal to sin phi by cos phi and this is equal to negative of omega L over r multiplied by square root of r square plus omega square L square divided by square root of r square plus omega square L square, and this is equal to negative of omega L divided by square root of r square plus omega square L square over r divided by square root of r square plus omega square L square. From where we'll get cos phi as equal to r over square root of r square plus omega square L square. We'll now substitute this in equation number 6 Therefore, the current amplitude I0 will be E0 over R multiplied by R over square root of R square plus omega square L square, and this is equal to E0 over square root of R square plus omega square L square. Now the equation for the instantaneous current is I equal to E0 over square root of R square plus omega square L square cos omega t plus phi, where the phase angle is given by tan phi equal to negative of omega L over R, or this is minus of tan phi equal to tan of minus phi equal to omega L over R, or the phase angle phi is equal to negative of tan inverse omega L over R. Here it is instantaneous current, so we have to write this as IT. Note that here the phase angle is negative. Note that the voltage waveform was E equal to E0 cos omega t. When such a sinusoidal voltage is applied across a series LR circuit, the instantaneous current IT is proportional to cos of omega t minus phi, because the sign of the phase angle is negative. What this essentially means is that in a series RL circuit, the current, the instantaneous current, lags behind voltage by a phase factor of phi. Let us now try to plot the instantaneous voltage and the current that is generated in the circuit. What is drawn in solid black color is the instantaneous voltage, that is E equal to E0 cos omega t. This is at t equal to 0 seconds. So the voltage is maximum at t equal to 0 seconds, and the current is maximum at say t equal to say 10 seconds, after 10 seconds. So that means that there exists a phase difference between the voltage and current waveforms, and the current lags behind the voltage, and the phase angle is given by negative of tan inverse omega L over R, and the quantity omega L, which has the dimensions of resistance, can be expressed in ohms, and this is called the inductive reactance. So we have seen that when we apply a sinusoidal voltage into a series RL circuit, we will get an oscillating current in the circuit, and the oscillating current will be lagging the voltage oscillations by an angle phi, where phi is the phase delay. When we switch on such a circuit, there will definitely be the presence of transients, but the transients dies out very fast when compared to the steady state oscillations in the circuit.